Hello and welcome back. Going to do a quick overview here of Chapter 5, dealing with atmospheric moisture and precipitation. This will be broken up into two parts, so this is the first part. Okay, so this chapter deals largely with water. You can see water H2O. So the molecule has one atom of oxygen bonded to two atoms of hydrogen, hence the two H's and one oxygen, H2O. That's what we're dealing with in its many forms. So we have three major forms. The ice form or solid form we call ice. The liquid form we just call water or liquid water. And then the vapor form, which is here. You can't see vapor. It's the water vapor form, the gaseous form. What you see up here is steam, and that's when the water vapor meets cooler air and condenses back, sort of like making a cloud. But steam you can see, water vapor you cannot see, but it has a tremendous amount of energy. Never put your hand right there, you'd know. So the three phases of water. Again, water vapor, liquid water, and solid water or ice. Let's start with ice. Ice is water in its most low energy phase. The molecules are not vibrating or colliding as much. In order to change the phase of ice to water, we have to add a tremendous amount of energy. We have to add energy to convert that ice, break the bonds, and move that into a fluid, liquid form. You know that process? It's called melting. If we went the other way, water in a liquid form, it has the molecules with their latent heat. If we were to release that heat and take that water to its ice form, the process of freezing would release energy back into the environment. So the energy would come out of the water into the environment, and ice would be left with its lower energy phase. So melting requires energy, freezing releases energy. Now, if we took that same water and we added more energy to the water, tremendous amount of energy, almost 600 calories per square centimeter, we would turn that water into water vapor. That change of phase is referred to as evaporation. So evaporation requires energy being put into the water, turning it into water vapor. And the energy, that hidden energy or latent energy, stays with the water vapor. If we went the other way and had water vapor and had it release energy, that same amount of energy being released to the environment, could turn that water vapor back into liquid water. Now we could also see ice turn directly into water vapor, especially in very dry areas like the Arctic or Antarctic or maybe in high elevations. We see ice absorb a tremendous amount of energy, skip the liquid phase, and go directly to water vapor. And the energy would be in the water vapor. Conversely, we can use the same term, sublimation, for water vapor turning directly into ice, like up in the sky when snowflakes form. We see that sublimation process occur. But the process is, though technically can be called sublimation, a better term these days would be deposition or even fusion. So the hydrologic cycle is going to be a little exploration of the water on the planet, where it comes from, where it goes to, and how it gets from one form to another. And that involves the processes of evaporation, condensation, advection, precipitation, runoff, ponding, infiltration, also known as percolation, into soil water and later groundwater if it goes deep enough. And then putting moisture back into the atmosphere can certainly be done by evaporation, transpiration, or evapotranspiration. Now, rather than go into that detail right now, I encourage you to look at a video I made that addresses that hydrologic cycle. So you want to do that now. And when you're done, you should have a good understanding of evaporation, transpiration, evapotranspiration, condensation, advection, precipitation, infiltration, runoff, and ponding. So I want you to visually understand these as well as put it into terms. One thing that wasn't clear, and maybe should be clear, is when water falls on the surface, it does try to make its way down gravitationally between the cracks of the soil and the rocks, etc. It can only go down as far as where below that point, all the cracks between the rocks and soil are already filled with water. So it can only build up to that level, and that level is referred to as the water table. Below the water table, the rocks and the soil and the sediments are saturated. Above that, we have air and water. So just water in the spaces between the water, below the water table, and air and water in the spaces between rocks above the water table. Of course, in a wet year, the water table will rise, and in a dry year, the water table will sink. So it goes back and forth with the seasons, as well as other factors such as when people drill wells into the aquifers that hold the groundwater and basically take too much water out. If we look at the surface of the Earth, we see that 71% of the surface of the Earth is covered by water. 29% is covered by land. So to get a complete understanding of the planet, you might want to not only take physical geography, but also take a class in oceanography to understand those environments also, give you a more complete picture. That's the basis of what I want you to know from this diagram, but it does tell us some other things too. For instance, of all the evaporation on the planet, 84% of it is done by the oceans and the seas. Only 16% of the evaporation, we should say evapotranspiration, is done by the land surfaces. And that makes quite a bit of sense. There's a lot more ocean, and it's made out of water, and it's a lot more easy to evaporate water from water than it is to evapotranspirate or evapotranspire water from wet land surfaces. Also, this tells us that most of the precipitation that falls on the planet falls on the oceans. 77% of all precipitation will fall over the ocean. So yes, it rains over the ocean. Only 23% of the precipitation falls over the land. And if you want to get a complete balance of what's going on here, the oceans do 84% of the evaporation. They get 77% of the precipitation. That's a difference of 7%. The land is responsible for 16% of the moisture in the atmosphere through evapotranspiration, but the land surfaces get 23% of the precipitation. Again, a difference of 7%. So some of the evaporated moisture from the oceans makes its way over to the land before it falls as precipitation. If we look at by volume now, where most of the world's water is, we can see that clearly the majority, the great majority, 96.5% is found in the forms of oceans and seas. Well, depending on who you ask, we have anywhere from 1 to 5 oceans. Some people say there's just one ocean, it's called the world ocean, and others break it up into segments. In geography, we like to break it up into the Pacific Ocean, the Atlantic Ocean, the Indian Ocean, and the Arctic Ocean. So 4 oceans. Others like to break it up into 5, and they include the ocean around Antarctica as a separate ocean called the Southern Ocean. And there's rationale for both scenarios. But the key here is that 96.5% of all the water on the planet that's available to us, not counting that's locked up in rocks, is found in the oceans and seas. By the way, seas are just parts of oceans. Now, glaciers and ice caps represent the second largest source of moisture, and that would be 1.7% of the total. So the great continental glaciers of Antarctica and Greenland are the biggest sources there, 1.7% of the total available moisture on the planet. We talked about soil moisture and groundwater before. Well, all that moisture below the ground represents another 1.7%. And that leaves only 0.1% for all the moisture in all the lakes, rivers, swamps, atmosphere, biosphere, etc. So that's very little of the water available to us. So review here, the oceans and the seas, these are going to represent basically 96.5% of all the moisture available to us. If you want to know, the largest ocean is the Pacific Ocean. It's on this slide too. The Pacific Ocean represents about a third of the surface of the planet. Just that one ocean. So somewhere around 64 million square miles of Pacific Ocean. The next largest is the Atlantic Ocean. That's about half the size. That's about 32 million square miles. Our third ocean is the Indian Ocean. That's somewhere around 28 million square miles. And our last ocean is the one up towards the Arctic. It's called the Arctic Ocean, about 5 million square miles in size. So the Pacific Ocean is about the same size as the Atlantic, Indian, and Arctic Oceans combined. And that means that the other third of the planet is the land. Thereabouts, you can tell I'm rounding off, but basically the land surface represents about a third of our surface of the planet, the Pacific Ocean about a third, and the remaining three oceans, the other third of our planet's surface. Again, rounding off quite a bit. Glaciers, again, 1.7% of the available water to us. There's the largest source, Antarctica and Greenland, and also the glaciers we get up at high altitude. We see alpine style glaciers. But again, 1.7% of all the water available to us, whereas the oceans and seas represented 96.5%. So again, oceans and seas, 96.5%, and that includes sea ice, by the way. Sea ice is not the same as glaciers. This is just basically frozen water on the surface of the seas or oceans. Whereas glaciers, those exist on land, representing 1.7%, and groundwater and soil water, so that's the water below the surface, which can be pumped up, represents another 1.7%. So it doesn't leave a whole lot left. That 0.1% for all the water in all the rivers, all the water in the atmosphere, the clouds in the atmosphere, all the water in all the world's lakes, including the largest lake in the world, which is the Caspian Sea. Yes, that is a lake, not a sea, because a sea has to be connected to an ocean. Caspian Sea is not. And all the water in all the plants and all the crops and all of us, that still represents only a tiny fraction of the water available to us. Okay, so the next section deals with humidity, and we're going to look more than anything else at something called relative humidity. And that's basically a comparison of how much moisture is in the air compared to how much moisture that air can possibly hold. So sort of like your gas tank in your car. If you've got a certain amount of gas in your car and your gas tank is a certain size, you can figure out how full it is. Let's say if you had 8 gallons of gas in your gas tank and your gas tank can hold 16 gallons. So if you've got 8, you can hold 16. That gas tank is halfway filled. Now we express that as a percentage by multiplying by 100. So instead of saying a half of a tank, we would say it's 50% full. Well, we do that in terms of the gas tank being the air. How much water vapor, not gasoline, but how much water vapor can air hold? But it's the same equation. The equation is relative humidity is equal to the actual amount of water in the air compared to how much water vapor that air could possibly hold. And again, we express it as a percentage by multiplying by 100. So the mathematical formula would be AMR, that's the actual mixing ratio, over SMR, the saturation mixing ratio, times 100. Okay? Now, the actual amount of moisture you have in the air doesn't change. Once you know how much is there, it's going to stay that amount until or if you evaporate more moisture into it, condense moisture out of it, or have it mixed with other air. Now, we're going to say, for all intents and purposes, once you know how much you've got, that's how much you got. Now, what does change is the SMR, the saturation mixing ratio, the amount of moisture air can possibly hold. So that equates to the size of your gas tank. Well, unlike a car, air's gas tank gets bigger as the air gets hotter, and it gets smaller as the air gets colder. So the ability of air to hold moisture goes up when temperature goes up. Increase the temperature, SMR goes up. Increase the temperature, SMR goes up. Increase the temperature, SMR goes up. So we have a good relationship here between, or direct relationship between the temperature of the air and how much moisture or how much water vapor that air could possibly hold. So remember, change the temperature, AMR doesn't change. The amount of moisture you actually have doesn't change, but the amount you can hold does change, and that's going to be important. Now, to really hit home these relationships, I've made another video, and I'd like for you to take a look at that now. So go ahead and review the video on relative humidity that's embedded in your Canvas class right now. Okay, assuming you've looked at that video on relative humidity, you might also be able to understand these next few slides here. First of all, I wanted to take a look at this red line. We discussed this in our prior chapter. This is the diurnal temperature changes, or the daily temperature changes that occur in air on average. And we can see that air gets colder and colder and colder and colder until early morning hours, we'll say right around sunrise. When the sun comes up, starts to warm the air, and the air at the surface starts to increase in temperature, reaches a maximum middle of the afternoon, we say 2 to 4 p.m. And then throughout the evening hours, the nighttime, into the early morning hours, the air temperature decreases again until the next sunrise. Now, because temperature gets lower in the early morning hours, that means that the saturation mixing ratio is also lower. The air cannot hold as much water vapor. And that means relative humidity is higher in those early morning hours. Now think about that. The air is more full of water vapor in the early morning hours. Well, when would you expect to see fog? Would that not be in the early morning hours when we get cold temperatures? When the relative humidity is the highest. In the afternoon hours, when temperatures at the surface reach their peak, we don't see very much in the way of fog because relative humidities are pretty low. Now, if you're really astute, you would also think, well, wouldn't that air get hot in the afternoon and rise and cool? And that is true. So in the afternoon hours, you probably won't see fog, but you may see clouds as that air has risen, cooled, and condensed up in the sky in the form of clouds. Okay, I'm going to end this little section here with an overview that we will come back to on the first part of section 2. And this is titled The Steps to Precipitation. In other words, how do we get precipitation? How do we get rain and snow and sleet and hail, etc.? Well, we have to start out with air that's at the surface or near the surface that has some heat, but also contains two very important physical attributes. And that is that the air must contain water. It must contain water vapor. Because if the air does not contain water vapor, you're not going to get clouds out of it, and you're not going to get rain out of it. The other thing that the air must contain is what we call hygroscopic nuclei, sometimes called condensation nuclei. Well, nuclei is like a small center. Hygroscopic means water seeking. Condensation means change of phase of water from a liquid to a vapor. So condensation nuclei or hygroscopic nuclei are required for clouds to form. That's just a fancy name for little solid particulate matter like dust or ice. So we have to have some dirt in the air as well as water in the air. Without those, we're not going to get clouds. So let's say we have some air and it's got some dust particles and it has some water. And that air has been warmed up and it wants to rise. So the next step is the air is going to rise or ascend and it's going to cool. So we get ascent and cooling. Well, as the air rises, it immediately starts to cool adiabatically. So it rises and cools, keeps on rising, keeps on cooling, keeps on rising, keeps on cooling. And at some point, it will get to the point where the AMR has finally met the SMR. So AMR and SMR become equal. At that point, condensation will begin. Relative humidity is 100%. The air is saturated. We have reached what's referred to as the lifting condensation level, and condensation has started. That means that the water vapor is now being booted out of the air in the form of little droplets. And those droplets stay in the air and they can't fall down because the air is rising from below. So they're being suspended there. And they will continue to be suspended until and if those droplets continue to grow. So little droplets of water hit each other and become bigger and bigger and bigger. And finally, if they do grow big enough, they will fall out from the cloud in the form of precipitation. So in order for precipitation to occur, and that can be rain, it could be snow, it could be sleet, it could be hail, it could be many different forms. In order for that to form, the droplets must have grown, the air must have risen to its lifting condensation level and its dew point temperature. Relative humidity must be 100%. In order for that to have occurred, the air must have risen, and it must have also contained water and condensation nuclei. So all these steps must have occurred in order for us to get precipitation. We'll talk about the forms of precipitation in part 2. So we're looking at it here. Condensation nuclei are very, very small pieces of dust. They allow tiny, tiny 0.02 millimeter average droplets of water to form in the air within the cloud, and those will hit each other, keep growing. They'll hit more and more and more until they grow big enough, maybe about 2 millimeters, for the average raindrop to fall. Okay, to wrap up here, we have air at the surface. Warms up, it's got some dust in there, it's got some water, and that air will rise and cool, rise and cool. So adiabatically cooling, rise and cool, rise and cool, rise and cool, and finally, boom, we can finally see at that point a cloud starting to form. Below this point, we can't see the air at all. It's all invisible. Now, finally, up here, we can see the clouds start to form because at this very level right here, at this lifting condensation level, that's the elevation required for the air to rise and cool enough for condensation to begin. It's gotten to a temperature. It's been cooling down, and finally reaches a temperature at which condensation begins. We call that temperature the dew point temperature. We know at this point right here, relative humidity has finally gotten to 100% because below that, it was less than 100%. Rising, but still less than 100%. Rising in relative humidity, but still less than 100%. And then finally, boom, at this point, relative humidity is 100%. So at that very same point, we've reached our dew point temperature. We've reached 100% relative humidity. The air is now saturated. We've risen enough to reach our LCL, or lifting condensation level. And finally, water vapor is coming out of the air in the form of droplets of moisture. And those droplets continue to come out, and they will grow together and coalesce. And if we're lucky enough, those coalescing droplets will fall out or precipitate out in the form of rain or sleet or drizzle or snow, etc. So we'll address the forms of precipitation in part 2. If you have questions, we're going to post them into the Canvas chat section. I will go over this in class on Zoom as much as possible, but this is here for you for a quick review, and hopefully that will clarify some of the things that might not have been initially clear when you read the textbook or went over the unnarrated PowerPoints. Okay, take care. See you soon.